having given me the opportunity of talking about relativistic hydrodynamics. Now, let me share my screen. Can you see my screen now?
Yes, absolutely.
Okay. So those of you who may have seen some presentation of mine may know that, you know, I tend to use relativistic hydrodynamics to study neutron stars, accretion problems onto black holes, and that, you know, normally these type of studies lead to very eye-catching and fascinating animations. And I will not present any of this today. And that's because, you know, this wants to be a lecture. So something I would be giving you if I was in Paris, and I'm very sorry we cannot be together in Paris, but if we were in Paris, I would be in front of a blackboard and try to explain to you not so much how you make a simulation on neutron star. That's something you will learn and hear a lot in the course of the conference. Rather, I want to spend some time and pass on some of the basic concepts of what is fundamentally important when producing those simulations that, you know, we present at conferences. So this will be a lecture in the classical lecture style after COVID, which is essentially online. And here is what I will be talking about. Can you see my screen move?
Yes.
Yes, okay. So I will first give you some basic concept on fluids. I will not go into the, you know, the very basic, but at least I will start distinguishing between dynamics and kinematics. And I will then talk about two important tensors that enter into this picture, which are the energy momentum and the current tensor. And then we will go on to hydrodynamics as, you know, a series of conservation laws, and hit the wall of nonlinearity. That is, we will find out some of the importance, some of the beauty and the curse of having to do with nonlinear equations. And as a final part, I will try and talk about the importance of conservative formulations, which are the ones relative to a numerical solution. So essentially, the first four bullets are not about numerics. The last bullet is about numerics, but I will not talk about numerical techniques. I will be talking again on mathematical aspects. So much of what I will present can be found in this book, which I've written in 2013 with Alindo Zanotti. All the material can be found in chapters 3, 4, and 7. I'm pretty sure you have a copy of this book in your library, but if you don't and cannot have a copy of a copy of it, let me know and I'll pass you over the relevant chapters. I cannot pass you the whole book because this would infringe my agreement with the publisher, but I can pass you the relevant chapters if you wish. And this is my time plan. I will be speaking for, well, till 5. Then I'll take a break with questions and answers of 15 minutes. Then once more, 1 hour of lecture, and then 15 minutes questions and answer. I don't mind being interrupted. And actually, it can be useful for two reasons. A, I make sure you're not sleeping. B, that helps me be sure that, you know, I'm still connected. So by the way, Guillaume, if for any reason my network, I'm at home, so if my network doesn't work well, please let me know and I'll look into this. Okay, so let me start. And this is really, you know, what I would be teaching you in front of a blackboard. So I'll be writing. So let's start with the kinematics. And of course, this would be followed by dynamics. So the most important quantity that we want to deal with in hydrodynamics is the fluid flow velocity. this is a rank 1 tensor, and I normally indicate tensors with a little bar under them. And if I want to write the components of this tensor, this would be just given by the variations of the coordinate of a fluid element along a given direction as a function of the proper time, where tau is the proper time, i.e. the time in the fluid's reference frame. So you have to imagine that there is a certain word line and that our fluid element is just moving along a fluid element and has a tangent vector to its word line, which is given by this 4 vector u. And you can think that this is a single particle, if that helps you, but you really have to think that we're dealing with a fluid here. So I am assuming that there is a certain volume, which I can define when there is a certain number of particles, and this number is actually extremely high. Talking about 10 to the 30 particles in any reference volume. And all of the properties of this fluid are continuum. So I can go in any position and I will not see any discontinuous function. And that's the fluid description. Okay, so this is a fantastically successful description, because with the same description, you can describe what happens when two nucleons collide at relativistic speed, or if you want to talk about large-scale structure in the universe, you're still using essentially the same description, a fluid description. Okay, so if another important quantity is the acceleration, kinematic quantity. Is the acceleration. And how do I define this quantity? Well, I define it as the convective derivative of the 4 velocity vector. So I take a nu, u nu, lambda nu, u mu. So this is the convective derivative of u itself. Okay, so it's convective because I'm taking a covariant derivative. By the way, this is a covariant derivative. I'm taking a covariant derivative along the fluid 4 velocity. I can also write it like so. A is defined as the covariant derivative along u of u. And if you remember, well, I don't know if you remember, but if you've ever seen, there is a class of integral curves of u such that nabla u is equal to 0. So these are the curves that parallel transport the tangent vector. Okay, why is this a parallel transport? It's a parallel transport because I'm taking the covariant derivative along u, and u, as we said, is a tangent vector. Okay, to the curve C. And what are these? Well, these are well-known curves. These are the geodesics. Okay, so we've just learned that a geodesic curve has 0 acceleration. This is something which is, possibly well known for if you're thinking about a particle, but this is true also for a fluid. Okay, so we defined A to be like so. Now, another property that is not obvious, but it is actually true and very important, is the following. A and U are orthogonal. So if I do and take a scalar product between A and U, I get 0. And you know, if you want to prove this, is very simple to prove, but you first have to prove that the following is true, which is also not very difficult. You have to prove that U nu nabla mu U nu is equal to 0. If once you've proven this, then it's trivial to prove that A dot U is equal to 0. So what does this mean? Since U is time-like, this implies that A is fully spatial. Okay, I recall you that, well, I should really write it here in the definition. U is a time-like unit vector, so U mu is equal to -1. Again, this is very simple to prove. If you remember that tau is minus d tau squared is equal minus ds squared. Okay, so what does this mean? It means that if I have U, then I can define a, let me use a different color. I can define an hypersurface which is orthogonal to U, and on this hypersurface I can define my acceleration A. And of course, U and A are going to be orthogonal. Okay, now why bother? Why should we pay so much attention to A and U? The reason is that with these two tensors, A and U, we can build we can essentially build everything we need to know about a fluid. So about the kinematic of a fluid. And if you spend 1 minute thinking about this concept, this is remarkable. We can say everything about a fluid, how it behaves, how it rotates, how it changes shapes, how it expands and contracts, only in terms of these two vectors. So let's see how we do this. First of all, let's introduce another vector, which is a displacement vector. Between two fluid elements. I hope my handwriting is not too bad. It's not easy to write on the iPad, and I want to go a bit fast today. So I have two fluid elements now. I call them A and B. I have a given displacement vector psi, and as before, I have my tangent vector U. Now, it's quite natural if you think about it. If you have two fluid elements, then the vector psi will be lead dragged along U. So naturally, psi is lead dragged along U. This is equivalent to saying that if I take the lead derivative along U of psi, this has to be equal to 0. And I am assuming you know what is the lead derivative, but if not, well, I will just give you a quick reminder. Lead derivative of U along U of psi, this is the commutator of U and psi. And if you think about this in terms of components, the nth component of the lead derivative of psi along U, this is nothing else but U mu nabla mu psi nu minus psi mu nabla nu U nu. And what we've just said is that this quantity is equal to 0, which means that if I now look at it and put it on one side the other quantity, I have that psi dot mu, which I define as the convective derivative of psi mu, well, this has to be equal to the convective derivative alongside of u mu. Now, seen like that, this equation is not a particularly telling, but you have to remember that psi dot mu equal a constant. So the integral curves of this equation are the fluid lines. Okay, so what we have just seen is that essentially by solving this equation, we can have information on the fluid lines. So fluid lines, I recall you, are these objects here, which I've just drawn here. These are fluid lines. These are the word lines of fluid elements. Okay, word line is the trajectory in space-time of a particle. A fluid line is the equivalent in the case of a fluid. And here is the important result that I was anticipating before. It's possible to show that the following is true. Psi nu nabla nu u mu is equal to this quantity here, omega mu nu plus sigma mu nu plus 1/3 theta h mu nu minus a mu u nu psi nu. Or if you want, equivalently, what we have seen is that we have decomposed this guy into this expression over here. So this is called the irreducible decomposition of nabla nu u mu, and hence of the fluid lines. So those of you who have, mathematical, a keen mathematical intuition can appreciate that essentially what we've done here is we have taken this object u, which we, can be as generic as possible, and we have calculated the covariant derivative in terms of this displacement vectors, and we have split it into some terms, and each of these terms has a meaning. This guy has a meaning, this guy has a meaning, and they are all functions of a and u, and they tell us all we possibly need to know or want to know about the kinematics of the fluid. Okay, so W sigma theta contain, let's say, all the information on the kinematics of the fluid. And what is this kinematic information? Okay, so far I've just said you take these guys, you split them, you obtain something else, but I have not given you any understanding of what these omega and sigma and theta and even h mu nu. I haven't told what it is. Are you still there? Or am I talking to my screen?
Yes. At least I can hear you.
Okay, thank you. As I said, sometimes I need to remember I'm not the only person speaking here. So we have to understand what these guys are. So and the best thing to do is start with definition. H is not a fluid quantity. H is called the projector operator. Orthogonal to to U. So by definition, H is defined, this is a tensor. Let me write it in component form. H mu nu is defined as G mu nu plus U mu U nu. And it's very simple to show that H dot U is equal to 0, okay? Let me just show this for you. H mu nu U mu, okay? This would be G mu nu U mu plus U mu U nu U mu. And this is just U nu because I've just lowered the mu index. And here now I have that these two will give me a -1, so I have minus U nu, and so this is equal to 0. So H is just a way of whenever I have a vector U, I can project in the orthogonal direction using H. Now, the first important quantity is this omega. It's called the kinematic shear vorticity tensor. And the definition, let me write it in covariant component, is the following: is the fully spatial projection of the double covariant antisymmetric derivative. Okay, so I have a antisymmetric covariant derivative, and then what I do is I just contract this twice with H so that I have a fully spatial object. So this would be alpha and beta, and this would be my H nu. So let me remind you so that you know what is the antisymmetric tensor. So this is H alpha mu, H beta nu, and then I have 1/2 of the covariant derivative along beta of U alpha minus covariant derivative along alpha of U beta. And I then have another tensor, which is sigma, and this is called the shear tensor. And by definition, sigma mu nu is the following: is this funny symbol, left angle mu u, right angle nu, and so this is by definition the symmetric covariant derivative plus the symmetric contraction minus 1/3 theta H mu nu, where if you want to write this in full, the symmetric is the same as the antisymmetric, but with a plus sign. So it's nabla mu U nu plus nabla nu U mu plus A mu U nu plus A nu U mu minus 1/3. Theta is defined as the divergence of the four velocities. So let me write it as nabla alpha U alpha H mu nu. Okay. I've defined theta to be nabla alpha U alpha, and this also has a name, and it's called the expansion. Okay, so once again, let me stress something already mentioned. In omega mu nu, as well in sigma, as well in theta, the only quantities I'm using, my building blocks, are just the velocity and the acceleration. And then I just play around mixing them in some shape, which is actually the most complete possible way. This is also called the expansion scalar, because it's a scalar function. Okay, I will not go into the details of what, these are, so this is a, let's see, this is clearly a symmetric tensor. Okay, so sigma is a symmetric tensor. by definition, okay, because I'm building it like that. And this is, by definition, an antisymmetric tensor. So what do these tensors mean, okay? You call them a shear, vorticity, expansion. How do we understand what they represent? I said they represent everything, okay? Whatever complicated fluid motion, you can decompose them into these basic pieces. So in order to see what is the physical interpretation of these tensors, let's consider a fluid element as represented by an ellipsoid. Okay, so you can imagine that a fluid element is just an ellipsoid, which I will draw like so. It's a completely generic ellipsoid, so you can have you know, axes which are not the same. Let me go from omega mu nu to a vector, because then it's easier for me to explain. So this is the vorticity vector. And the vorticity vector is defined as the dual of the vorticity tensor in the fluid frame. So it's the dual of omega mu nu in the fluid frame, which means I contract this dual of omega in fluid frame. And just so that you know what is my definition, this is 1/2 epsilon mu nu alpha beta omega alpha beta u nu, where epsilon mu nu alpha beta is the Levi-Civita tensor. Okay, so this is a vector, and this is fluid element, or a reference fluid element. So the idea is I take any of these. If I take the fluid, my reference fluid element, the vorticity tensor will tell me about the possible rigid rotation of my fluid element. So let me say that I will have a certain rigid rotation with a given, let me use a little omega. Okay, so out of my 4-vector little omega, that's a 4-vector I introduced before, out of this guy over here, I can build a 3-vector, and I can use this 3-vector to find out about possible rotations of my fluid element. So if you want to think about, say, turbulence, and you want to describe how much is a fluid element, undergoing a certain vertical motion, well, then you are going to give a certain number to this little vector here, omega. For the same reason, you have to think that, so let me say that this is vorticity if you apply the shear, what you will have is that instead of having your, yeah, I cannot do this quite easily, but you have to imagine that you have your reference, fluid element, which is an ellipsoid, and that now you actually distort it in some shape or form. Okay, so you can distort this object into something else. Okay, and you do this in terms of the shear tensor. So the shear tensors measures changes in the ellipsoid axis while preserving the volume. Okay, so you are really preserving the volume. You're not changing the volume at all. You can just change the shape. Imagine again, take a drop of water and you distort it somehow, maybe because you are in outer space. So this measures rigid rotations. And what is the expansion? So that's our last tensor to discuss. And here, the idea is that you can go to something which is either much bigger or much larger, and you can do these changes. You can either become larger or smaller depending on your physical conditions, and you do this but without changing the actual shape. So these are distortions. So this is the expansion. Measures changes in volume, but not in shape. Okay, so shape is a property of the shear. Expansion and sorry, you preserve volume, and so you can change this through the expansion, while you can change shape and preserve volume with the shear. And that is why I was telling you that with this decomposition here, this decomposition is so nice because it tells us all we need to know. Okay, all of the information is there, and of course it doesn't have to be all of these components don't have to be non-zero. Okay, if you think about a fluid which is isotropically expanding, okay, then there is no vorticity, there is no shear. For instance, if you're thinking about cosmology, that's the only thing that happens is expansion or contraction. But in general, in a fluid, you have that these are the basic aspects. Okay, so let me ask you, are there any questions on that?
Yes, actually, you had small questions concerning terminology in particular. So someone asked if the decomposition you just discussed was precisely the Rezzolla equation.
Yes, well, the Rezzolla equation, the Rezzolla equation uses this decomposition. Yeah. Then I see 1/2 in front of the entire one. So maybe I made a mistake. Which one is? What is the?
I'm not sure. I didn't see the question
is
immediately.
Precisely this equation that you have in front of you. I think you need to close the parentheses before the -1/3.
-1/3.
I think you need to close the last parenthesis before the -1/3.
Yes, indeed. It's a problem of parentheses. I think it's the equation just after sigma mu nu, the line after the equality defining sigma mu nu.
I'm trying to. So you are talking about a definition of the shear?
Well, the explicit expression you wrote just after the.
It's not okay. This is not a. This is a. Just to be clear. This object is not a round bracket. Is a left angle.
Yeah, but I think the question is that there is a minus 1/3, but inside the parentheses, for instance, and not. And, okay, I don't know. And there is the global 1/2, and it looks strange.
You're right. Sorry.
Okay.
Now I can see it. It's here. Okay. Very good. Thank you, Jeremy. So I hope I have impressed that U and A are quite interesting tensors. So U, A are basic building blocks.
Yes, there was a last question. Whether omega is a rigging tensor.
A rigging tensor. I don't know.
A rigging, sorry. Neither do I. So I.
Okay. It's a vorticity tensor. No. Omega is a vorticity tensor out of which you build by contracting, by evaluating in the fluid frame, a vorticity vector. Okay, you kill one index, and that's the way it is normally referred to. I never heard it about rigging. Are basic building blocks of kinematics, of fluid kinematics. And okay, but life is more complicated than just kinematics. You would like to have dynamics. So in dynamics, there are two more basic building blocks, tensor. And these are called J and T, okay? This is the four-current density. And this is the energy momentum tensor. So the question is, how do we define J and T? There are two different ways you're going to get exactly the same answers, okay? There is one first way, which is, if you want, more fundamental, and it makes use of Boltzmann equation. Okay, so imagine that you have a Boltzmann equation, which is a conservation equation for the distribution function. Okay, so it's something of this type. So P mu defined like M U mu is the form momentum. And F is the probability distribution function or distribution function of a set of particles with rest mass m. And the right-hand side is called the collisional integral. So if you have F, if F is known, then one can build a hierarchy of moments. One can build a hierarchy of moments. And in particular, the first two moments are the ones we're interested in, okay? So we would define the current as the first moment, so P mu F integrated over the invariant element in a momentum space. And I can think that this is, a certain number density times for vector and mu. And T mu nu, this would be the second moment. So this would be M P mu P nu F, again integrated over D3P P naught. And you can define all the other moments, but as I said, the building blocks for us are J and T. That's the first route, which is not a route I would follow here. The second route is maybe a bit more physically motivated, and the one I like to think about, where my brain it's easier for me to think about. So what I want is a tensor that is symmetric, a rank 2 tensor that describes everything I need to know about a fluid. I need a symmetric rank 2 tensor that collects every information on the energy momentum of the fluid, and this is my T, and I need a rank 1 tensor that tells me about currents. Okay, so I start, and this is J. I start from the latter because it's easier, right? So I can just say that J will be the product of the rest mass density times a 4 velocity, okay? Rho is the rest mass density. Or if you want, I can define these as a number density times the mass of my particle. For T mu nu, well, what is it that I want? I have a rank 2 tensor. And so I have 16 entries. And some of these will be fully spatial. Some of these would be time, space. And there's going to be one which is going to be time. So what I could think of is that this tells me about the flux of the mu momentum density
Luciano, so I interrupt you because you have notational questions. So people want to know what are P0 and mu, sorry.
Okay. Yeah. You have to tell me, Jerome, if there is a question, because I don't see them. I don't see when they appear. I can see them.
Yeah, it was just above.
Where do I see them?
It's in the chat, I think. If you
Yeah. Now it's finding the chat that is problem. Okay.
Ah, you have lost your chat. I see.
P0 is the momentum, time or space. Okay, I see that Luis Longo is asking if omega is a rigid vector in the sense of allowing precession. Yes, it is a rigid vector. It's talking about rigid radiation. P0 is the little p. I have said that P, what did I say, is a 4 momentum, okay? And so P0 is just is what I would call otherwise PT, or if you want, this is what I mean. And N mu, well, you can think that this is, if you think that this is also N M u mu, okay, then you have the answer to your question. So N mu is the number density current. Sorry, it's the is this quantity here, mu. I don't know what is the number, the name of this. But you can think that, yeah, well, this is the momentum. Let me just double check one thing. Yeah, so this is it. It's a different way of writing the momentum. I assume this answers the questions, and I'll move on. So I have made this definition. This is the definition. And now I try to build this object. So let me get rid of a few things. So I will first consider the T00 component. So actually, let me get rid of this. So this is the this would be the 0th momentum component in the time direction. And this is just the energy density. Okay, because if you think about it, this is just the energy, the flux of momentum in the time direction. And the 0th component is the energy. The 0 component of the momentum is the energy. I can take now the T0I, and this would be the energy flux. Okay, so this would be the 0th component in ith direction. I can take the Ti0, and this will be the momentum density. So this would be the ith component of the momentum in the time direction. And then I have the fully spatial part. So Tij, this is again a momentum flux now. And so this will be the ith component in the jth direction. So if I, because this is a tensor, and let me just get rid of this. I can this is I can represent these as a matrix, okay? And I can think that I have (16) slots here. So this would be T00, this would be T01, this would be T02, T03. I take the symmetric part, T10, T20, T30. I take the diagonal, T11, T22, T33. And then I take T21, T23, T31, T32, T12, T13. So let me let's collect the different pieces, okay? This is easy to do this with colors. So this here is the energy density. Is the T00 component. These guys over here, let me do it orange. These would be the energy flux, energy fluxes. These are the guy here. These would be the momentum densities. And well, what are we left? We left with this guy over here, the spatial part. And these are the momentum fluxes. And in particularly important are these guys over here. We will see them later on, the diagonal parts here. Okay, so what we've done is we've just said, okay, we want to have a tensor, this guy over here. It seems this tensor does have all the components that I need because I have something that tells me about the energy density. If there is an energy flux, energy is going in one direction, then I have an energy flux. If I have a momentum flux, then I can describe it. And I have, well, these are just the different way of looking at the energy fluxes. So we have all we need. We now have to fill in these slots with something we understand, physically motivated. So to fill in these slots, we can think of going in the only frame where all of these quantities are well defined. Okay, if you think about it, even the first one, the energy density, what does the energy density mean? If I am in a frame which is moving relative to a fluid, then the energy density is not necessarily the energy density in the fluid itself. It will also suffer from the boost that I am experiencing because I am in a relative motion with respect to my fluid, okay? And this is the fluid rest frame. So in this, this is also sometimes referred to as the co-moving frame. Okay, so in the co-moving frame, we can hope of making some sense out of this. Then I know that the energy of a particle, I mentioned this, but I'll write it again. Energy of a particle is E equal P naught, the upper contravariant component, the time component of the momentum. So if I have many particles, I can think that T naught naught will be equal to the number density time an average of all the energies of all the particles. Okay, why do I need a number density? Because it's an energy density. It's not an energy. So it's not just N, capital N, but it's N over a volume. And so this is the energy density. I average energy of all particles. And to remind myself that I am in a co-moving frame, I'm putting these little hats. Okay, so we have a first slot for this guy over here. And I'll give this a little letter E. Then I have the T0I and the TI0. And these are, as I said, the fluxes of energy. If I am and here is an important definition. For these quantities are 0 for a perfect fluid. So this is a fluid where there is no dissipation, no energy flux. So then I have Tij. Okay, this is so this is, as I said, this is equal to 0. This is also equal to 0 if I is different from j. So away from the diagonal, I have that these quantities momentum fluxes are 0. So a perfect fluid is a fluid satisfying these definitions. And the last piece, which I haven't said, is TII. And I also give a letter to this quantity. So this is the momentum flux, is the ith component of the momentum in the ith direction. So, and I call this isotropic pressure. So if I go back to this scheme over here and I try to get a copy and get rid of what I don't want to see. The energy momentum tensor of a perfect fluid in the co-moving frame is particularly simple. Okay, I have essentially is all 0. Oops, didn't want to do that. Apart from the diagonal terms, and these are the energy density and the pressure. Okay, so this is the energy momentum tensor. And okay, but I've given you a matrix representation. Now I want to come up with a tensor representation. That's not difficult. A tensor representation is not difficult to obtain. And, you know, in the co-moving frame, u mu is just u mu u0 0 0 0, or if you are in special relativity, this would be just 1 0 0 0. So I can say that T mu nu as a tensor can be written as E u mu u nu plus P eta mu nu plus u mu u nu, and this is a tensor equation. This tensor equation has to be valid in any frame, not necessarily in special relativity. And so I have that my definition of the energy momentum tensor is the following: E plus P u mu u nu plus P g mu nu. Okay, so this guy together with my other guy, which I've defined before, rho u mu, are my building blocks of the dynamics of fluids. So these are the building blocks of hydrodynamics.
Luciano?
Yeah.
If I may pose a question here, did you at some stage implicitly assume that this co-moving frame is an inertial frame, or it makes no difference?
Well, yes, I was working in special relativity at one point. So, you know, the co-moving frame is an inertial frame. But, you know, I needed this just to come up with this expression over here. Once I have this expression, this is a tensor equation, so it has to be true in any frame, and that is why I can write the energy momentum tensor in this form.
Luciano, you have also a question about what is the perfect fluid. Is the perfect fluid just mathematical convention to make the problem simple, or do we have a real fluid which is not perfect?
Oh, yes. Okay, so I will come to these questions in a second. Let me just finish this sentence. These are the building blocks of the dynamics of fluids of fluid dynamics. So to answer the question about perfect fluid, so you know you can work mathematically and say these are the definition of perfect fluid. Fluid is such that these components are zero. What is it that we are ignoring by setting to zero these components? We are ignoring energy transfer. Okay, energy transfer, to give you an idea, is if you take a fluid and there is one part which is hot, another part which is cold, the energy will want to flow from the hot to the cold without any motion of the fluid. In this description of a perfect fluid, this cannot happen. The only way in which energy can go from hot to cold is if really the fluid is moving from one portion to another. Another aspect that we are ignoring is when we set to zero these guys here, maybe I haven't, when setting these guys to zero is meaning that I don't have any cross exchange of momentum. So I don't have, for instance, any shear. And a fluid which is perfect doesn't have any of these effects, and so doesn't suffer of any dissipative term. So this is another way in which people normally think about perfect fluid. Perfect fluids are fluids that are inviscid. There is no viscosity, either bulk or shear viscosity. Okay, I hope this answers these questions. I want to say a few more words, and then we break for a few minutes. Well, no, I said
Luciano, still in this question about the perfect fluid, there is any physical situation where this is a good approximation, or this is just a proof of concept of the theory?
No. So first of all, where you are breathing a fluid which is not perfect. And most of the fluids that we know of are imperfect, but mathematically they are much easier to treat, perfect fluids, and there are physical conditions where the use of perfect fluid is a reasonable approximation, because what you are ignoring would manifest itself as a change in the fluid properties on a much longer time scale. I'll try to give you an example which is maybe useful. Think about neutron stars merging. Strictly speaking, they are not inviscid, but the amount of viscosity is so small that it would come up as a change to your perfect fluid picture only if you were to look at changes in these configurations over many millions of years. Because we're not doing simulations over millions of years, it's a reasonable approximation to treat them as perfect fluids. Having said that, it's all a matter of, precision. And that is why people, me included, are looking at formulations of the hydrodynamic equations that do contain these terms. Even if they are small, it's always nicer and better to solve a set of equations which is as complete as possible, knowing that there are terms which are included that are not very important, but still are providing the full picture. Does this answer your question?
Yes, it does. Thank you.
Yeah. And this concept actually can be carried out also in case you have magneto-hydrodynamics, so the extension of these equations to the presence of electric and magnetic fields. There too, you can think about conductivity, electrical conductivity, and consider a fluid with infinite conductivity, and that's the ideal MHD limit, or a fluid with a non-infinite conductivity, then you're talking about a resistive fluid. Once again, most of the time use ideal MHD, but sometimes resistive effects are actually important. Okay, so since we are, what do we do with these guys here? Okay, so we have, so far, I've just told you that T and J are important. I've explained what they contain. By the way, look at this guy. This is quite amazing that this guy, a single tensor, has everything you need to know about energy and momentum. In standard classical hydrodynamics, we distinguish momentum and energy, but here everything is in a single tensor, so quite nice. What do we do with these equations? What do we do with these tensors? Well, you could say, actually, I don't know. Or you could say, well, I know that these quantities, these tensors are representing, actually follow conservation laws. They, if I think about, what are the microscopical elements of this fluid, these are particles, and particles are known from mechanics to conserve energy and momentum. Okay, so in principle, what we would like to have is we would like to write conservation laws for these equations. We know from other considerations that the energy, well, the rest mass, let's start from there, the energy and momentum of these tensors are conserved. And it's natural to assume that also J and T need to satisfy conservation laws. And how do we write these conservation laws? Well, this is very easy. You can show, okay, if you take a volume integral of a four-dimensional piece of a manifold, and you impose that there is conservation of any quantity, then you will find out that this is just using Gauss' theorem, that this is equivalent to setting the divergence of this quantity you want to conserve equal to 0. So this is the rest mass conservation. And I have another set of equation, which is the following. Nabla mu T mu nu is equal to 0. This is energy and momentum conservation. Okay, so these are the two equations expressing the dynamics of fluids. And I will stop here to take some more questions, or if not, to have a few minutes break.
Yes, there is one more question in the chat, if you can see it. So what are the consequences in T mu nu if G is a semi-Riemannian metric?
I'm not sure I understand the question. So, David, can you express it in a way which is a bit clearer? I haven't made any assumption on G inviting my T mu nu. As I explained to you, what I've done is I have gone into a fluid frame, and I've tried to define quantities that are made physically easy or physically well defined, which are the energy and the momentum flux. Then I've tried to come up, this expression that I have here is just a way of representing this tensor here, given this frame over here. So I'm not making any assumption on the properties of what is G. Does this answer your question? David. Okay.
Okay, very good. So are there more questions? Yes. Ilsa Yoon, you can.
Yes, please. Oh, turn on your camera.
Can go on.
Who you are.
Hello? Hello?
Yes. Yes, we can hear you.
Yeah, thank you. Yeah, I'm sorry, because of the bandwidth, I usually having a problem with to turn on the videos, so sorry about the camera, but I would like to ask this question. First of all, thank you very much for this nice introduction. I really like this format of lectures. And this is actually the follow-up question that I already asked about a perfect fluid. So as far as I understand, you decompose the kinematics of the fluid into vorticity and the shears and the contraction or expansion. Then you introduce the dynamics, which drives the kinematics of the fluid. Then those dynamics tensor does not have the energy transfer without kinematics. So am I right in terms of understanding that to make this consistent, we don't really have to assume the non-perfect fluid, which, as you mentioned, the energy is transport without kinematics? Or is my question clear? Or
yeah, I think your question was clear, but I think we should look in a direction which is slightly different from the way you are thinking about. Kinematics is telling us about positions. Think about the actual origin of the word. It's just telling about position. Now, kinematic in a fluid is telling, given a fluid velocity, for velocity, what are the properties? Can you say, how can you describe the fluid for velocity? And this is what the kinematics description, in particular, these nice tensors tell us about. It's a way of understanding, what the fluid looks like. But as in kinematics, there is no information here that tells us why a fluid should be distorted or expanding or rotate. It's just a way of describing it. If you want, it's a vocabulary. Okay, it's setting a set of words which we can use to describe a fluid. The dynamics instead, the dynamics is here. I've just introduced this. Is telling us that if a fluid has things like mass and energy and momentum, these quantities have to be conserved. And how do we do this? Well, we conserve. We know how to write a conservation law, and these are the quantities that we have to conserve. Two tensors, one which is the current, and the other one is the energy momentum. And these are going to tell me how a fluid will rotate and be distorted and be expanded and so on. It's through this equation that I will find out what happens to a fluid. Is this clear now?
yes, thank you very much.
Yeah. There is another question by Cyril Pitrou.
Yes, I have a question. And when you define the stress energy tensor and you perform an integral on phase space, this d3p divided by p0, is it defined in any coordinate system, or is it just defined when you have a tetrad? That is, this d3p and this p0, are they only defined when there is a tetrad, or is it general and you can define whatever the coordinates?
So you know, that definition of which I brought in is actually a special relativistic, so relativistic, but special relativistic definition of the moment.
Okay, so
Yeah. So I have made a very specific choice of coordinate. You can repeat this in
Okay.
relativity. It doesn't look pretty, and that's why I haven't done it.
Okay, good, thanks.
All right. Let's take 3 minutes break. So we reconvene at 17:21. Just
Perfect. So see you in 3 minutes.
yeah.
Okay, we are back. I think there was a last question, actually, we forgot to answer. So we can start with that, perhaps. If it was by Dongmo Safak Cosmos. So if you can speak.
Yes, thank you. Hello, everyone.
Hi.
Hi. Thank you for sharing this wonderful school with us. I have a question concerning the fact that since U is a timeline, why this imply the fact that A is space-like? Is it because A is defined as the convective derivative of U? Could we have more explanation about it? Thank you. This is my first question.
You know, it follows from this condition. A and U are orthogonal.
Okay.
Now, imagine you are in a moving frame so that U doesn't have any spatial part. Okay, then
Okay.
implies that A has to be, you know, will have a kind of spatial component.
Okay, that's right. And for the second question, due to the literature, I've currently seen the fact that when defining the energy momentum tensor, T nu mu, concerning the last question we wrote, I already see minus P times G nu mu rather than plus P times G nu mu. About the expression of the tensor, the energy momentum tensor. For this has been seen, for example, on the paper written by Babichev in 2004 about concerning the perfect phantom energy as a fluid in relation between phantom-like energy and black holes. So even here there was minus P times G nu mu.
Oh, I see. Yeah. So you know, I'm using a signature which is minus plus plus plus. And I don't know what is the signature that was used in that other paper. It is possible that they use a different signature, which might lead to a different sign here.
Yes, that's true, because when I see the metric, it is plus, minus, minus, minus. Thank you. This is what I see about the metric of Schwarzschild black hole.
Yeah. So
They choose minus, plus, minus, minus.
Okay. Let me continue. And I would like now to ask myself the following question. So let me give these 1, 2. Let's me now number these equations. 2 is expresses rather conservation of energy and momentum. These are 4 equations.
Sorry, Luciano, what is 2? Just to...
2 is this one.
Okay, thank you.
Okay. And so the question is, these are 4 equations. Why are they 4? Because I have that these index is free, and so I have 4 slots for new. And the question is, how do I distinguish energy conservation from momentum conservation? I know that there are 2 distinct equations. Well, 2 sets of equations. One is 1 and the other one is 3, because the momentum is the 3 vector. So the way to think about it is that the best way to think about energy conservation is by being in a in a frame which is co-moving with the fluid, because there the energy is well defined, and I can therefore define the conservation of energy relative to that frame. So energy conservation is naturally defined in the co-moving frame. When I move with tangent vector u. And so what I can think of doing is I can take nabla t, which is the conservation of energy and momentum, and project it along u. And this will provide me with the energy conservation law. For the same reasons, well, for the complementary reason, the energy momentum, the momentum conservation equations are those in a frame that is orthogonal to u. And how do I do this? Well, if you remember, somewhere at the beginning, we introduced this guy here, the projection tensor, okay? So what I can do is I can go back here and do exactly the same I've done here. And now project along H. Okay. And these would be my momentum conservation law. Let me call this 3, let me call this 4. Okay. 3, you have to read it as u nu nabla mu t mu nu equals 0. And 4, you know, if you want to see this in component notation, this will be h alpha nu nabla mu t mu nu equal to 0. Note that alpha is really alpha h is a purely spatial tensor, so you just have 3 components available. So this is one equation, and these are 3 equations. So if you want a geometric representation, which I think is always a good idea in relativity, and if we have a certain fluid lines, then at any time, let me use the same notation as before, I have a tangent vector u. I have a certain tensor t, and I'm taking the 4 divergence. Let me say this is my nabla t, and I can define at any time a, you know, an orthogonal surface. And on this orthogonal surface, I can calculate, let me use a different color. This will be h nabla t. And along this other direction, let me use another funny color. Here, this would be u nabla t, okay? I don't know if this helps you, but this is a geometric representation of those equations. Okay, let's continue on this theme of the hydrodynamic equations, and let's look at a bit more in detail to these equations. So let's look at more detail to one. Okay, one, if you remember, is this equation here. Nabla mu j mu equals 0, which means u mu nabla mu rho plus rho nabla mu u mu is equal to 0. But this guy is also the expansion. So this is equal to say that u mu nabla mu rho is equal minus rho theta. So this is a different way of looking at the continuity equation. This is also called continuity equation. Let me number 4, 5. The equation 2, I can also write it, so actually, I can also write it as nabla mu of, I write T mu nu in a way which is somewhat different. I write it as rho h u mu u nu plus p g mu nu, where h is called the specific enthalpy. And so H is defined as the sum of the energy density plus the pressure over the mass density. And I can also write, if I say that the energy density is the sum of two components, one which has to do with the rest mass and one which has to do with the internal energy, rho epsilon, I write this as 1 plus epsilon plus p over rho. So this is the energy density, and epsilon also takes the name of specific internal energy. Don't get confused. This is the energy density. You take a bunch of particles, they have a certain energy density. And part of this energy density has got to do with the fact that they simply have a rest mass, but they also have some internal energy. They may have a certain temperature, if you think about a fluid, okay? And this is given by this quantity here. So think about temperature. So let's calculate what is this quantity. Let's calculate h dot nabla mu, sorry, nabla t equals 0. So in component notation, this would be something like h nu lambda nabla mu t mu lambda. I'm using some more different indices than before because, sorry, this is a lambda. So this will be, let's write this. It's h nu lambda. Let's take the covariant derivative of this expression here. And so we will have u lambda u mu nabla mu of rho h plus rho h u mu nabla mu u lambda plus rho h theta u lambda plus g lambda mu nabla mu p. And this is very easy now to compute because if you remember, h dot u is equal to 0. So this guy is 0 because I'm contracting lambda and lambda. This guy is also 0. So what I'm left with is the following: rho h u mu nabla mu u nu plus h nu lambda g lambda mu nabla mu p, and that's to be equal to 0. Okay, let me write this in a different form. So I have u mu nabla mu u nu is equal to minus h nu lambda g. Actually, I get rid of this as well. So I just have the following: u nu nabla mu p over rho h. And this is an equation which is worth a box. I don't know where I got to, 5, so let's call this 6. So does any one of you recognize this equation? This is a rather interesting equation, because if you remember, that was a few hours ago, no more than one actually. We know what this guy is. This is the convective derivative of the velocity, or for velocity. So this is just the acceleration. So what we have found is that the acceleration in a fluid is equal to minus this quantity here. So if you want this would be g mu nu plus u mu u nu nabla nu p, and let me write it as so. Okay, and this is equal to 0. So there is no acceleration if p is equal to 0, or if the gradient of the pressure is equal to 0. Okay, so think about what is called as dust fluid. Okay, a dust fluid is a fluid where each fluid element moves along geodesics. And why is it geodesics? Well, again, no more than an hour ago, we've seen that a fluid line with 0 acceleration is a geodesic. Okay, what about the other equation?
Sorry, before you go on, there was a question about the epsilon. So the question was, sorry, is epsilon interaction energy?
I have no idea what the interaction energy is.
So you can maybe develop about the physical interpretation of epsilon.
Right. So epsilon, if you think about a classic gas like the one you're breathing right now, this is directly related to the temperature. Okay, it's a different way of expressing the temperature. In the case of a classic monatomic gas, I think it's has to do with the Boltzmann constant. The two are related. So is a way of expressing. So in simple classical fluid dynamics, you have to think that particles that make a fluid element not only are moving or are static, but they also have some certain internal motion. And this motion, this agitation, this is essentially what manifests itself as a temperature of the fluid. And so maybe this will become clear when we compare with the Newtonian expression. Epsilon is a measure of this level of agitation. It's the energy associated with the fact that the fluid is not at rest, but has internal energy. And it's specific because the product of epsilon with rho gives me an energy density. So just to be clear, rho epsilon is the internal energy density. Okay, I need to move on, otherwise I will not be able to do what I want to present. So let's go to the other equation that we want to look at, the energy equation. So U nabla T is equal to 0. This is, I can write this as U mu nabla mu E, the energy density, plus rho H theta equal to 0. And, this is already quite, telling as an equation. Because if you think about it, this guy is telling us about the co-moving changes of the energy density, and it's telling me that these changes are related to theta. So if I take a fluid element and I compress it or expand it, then I will inevitably change its energy density. It's quite obvious, okay? And is, very neatly described by this equation. This you can also, using continuity. Did I give a number to that? No. Using 5. I don't know where I got here, 6. Let me call this 7. Using 5, you can also write this as U mu nabla mu E is equal to minus H U mu nabla mu rho. So this is a compression. So how do I don't know how many of you are familiar with the equivalent equations in Newtonian physics. So what are the equivalent equations to 5, 7 in Newtonian physics? Does anyone know them? I hope you do. But 5 is equivalent to the following equation, is the continuity equation. Sorry. dt rho plus d nabla I. So this is really a divergence in Newtonian physics is equal to 0. This is the continuity equation. Um, 6 is equivalent to dt vi plus vj dj vi is equal to minus 1 over rho nabla I p plus nabla I phi. And these are called the Euler equations. This is a external potential, for instance, gravitational. Let's see. And then 7, I will discuss them in detail in a second, but I just want first to write them. dt of 1/2 rho vi plus rho epsilon plus nabla I 1/2 rho vi plus rho epsilon plus p vi. This is equal to minus rho vi grad of phi. And this is the energy equation. So let's see if we can, okay. This is one of the things that I can do on an iPad I couldn't do on the blackboard, but since I can do it, why not do it? I will just copy it so that we can see them side by side. Okay, so you can imagine that here, the time derivative is contained over here, and this 4 divergence is contained in this 4 divergence. The principle is the same. If there is a time variation in the density, this is because you have a change, you have a net flux or a net current rho vi. Let's do the same here. Let me pick up the other equation. I will pick this one here, this 4. So, okay, in the Newtonian expression, I have a bit more than I have in the general relativistic one. Well, it's hidden. But these guys over here, they are these guys over here. Then we have the pressure gradient and the pressure gradient. They are over here. And where is the gravitational potential here? Well, don't be fooled. The gravitational potential, and this is the beauty of it, is already in the covariant derivative. Okay, so here you are taking into account the fact that the space-time is not flat, and there may be a gravitational potential, what in Newtonian gravity would appear as a gravitational potential. Okay, this is a comment that I will make. You will not understand. Maybe later on you will. This term here is a nonlinear term. This is responsible for the nonlinearities in the hydro equation. Is this very term, the orange one, that is responsible for all the beauty and the headaches of hydrodynamics. And I do the last comparison. I think I will take actually I will take this guy here. Here too, you have to see the analogy. Okay, this one of these components here takes into account both the time derivative and the spatial derivative, and essentially are saying you have to conserve energy in time and space, and this can change only if there is a compression or an expansion. Okay, this is the expansion. Okay, are there questions on this equation? No questions.
Well, yeah, I think there is a question. Is there a free index on the right-hand side of Newtonian equation 7?
No. This is a single equation, okay? So, well, yeah, I should have remarked this. If you look at this, what is this? This is the kinetic energy density, 1/2 v squared times m, but it's a density, so it's rho. So this can only be one single equation. That's why all the indices are contracted, and this is why the indices are contracted. It's a single equation. On the other hand, this is true also here, you know. Also, this one is a single equation. So it makes perfect sense. But this question is useful because it allows me to ask another question. Maybe let's see how many equations we have. So 5 to 7 are 1 plus 1 plus 3, 5 equations. Now, how many equations, how many quantities do we have? That we want to solve for? Well, it's easier if we think in terms of Newtonian hydrodynamics. So we have rho, we have three components of the velocity, we have the pressure, we have the internal energy, the specific internal energy. So it's 1 plus 3 plus 1 plus 1. So these are 6 equations, 6 quantities. Okay, either I made a mistake and I've lost one equation somewhere, or there is something that is else that is needed. If we were live, I would ask you, what is this? I don't have this option, so I will just give you the answer. This means that the system 5,7 is missing one equation that needs to be provided extra. And this equation is called the equation of state. That is a relation that allows me to write an expression of the pressure in terms of the density or of the specific internal energy or of the composition or whatever. Can be a simple or a very complicated expression, but it is an expression that allows me to close the system. In this way, the system can be closed. And specifying this equation, which is as important as all the rest, is this deserves a number 8. You will learn probably during these lectures or at the conference later on that the equation of state is a fundamental piece of information when we want to describe reality. Say an equation of state is needed for describing how two neutron stars merge, because their dynamics will differ if we have different expressions for 8. And this is true also if you're thinking about cosmology. We're not talking about cosmology here, but in cosmology too, you need to know how to relate pressure and other quantities. This is because the Einstein's equation, Friedman equations, do not tell you about that, or the hydrodynamic equations do not tell you about that. So there too, you need to have an expression, and in cosmology, you can be very wild, and you can just say P is a function of the energy density. Actually, it's related to the energy density times a constant. Okay.
Yeah, before you go ahead, there was a question. Someone wanted you repeat the argument about the counting of the equations. The question was, I lost the argument why 6 and 7 have 1 and 3 equations. Can you repeat that, please?
I lost the argument why 6 and 7 have 1 and 3 equations. 6. So let's go back to. So 6 is this guy here, okay? And you have that this index is matched with this index is matched with this index, and so the only free index that you have is this guy here, is nu. And you could say, haha, then it's 4 equations. No, it's not, because H is fully spatial. So you have to think that N can only be 1, 2, or 3. And when you do this, then you have just 3 equations. For 7, I think this is maybe self-evident, but let me again, you have here in component forms, you would have u mu nabla nu t mu nu, so equal to 0. This is a single equation because there is no free index. This guy is contracting with this guy is contracting with this guy. You don't have any free index. That's a single equation. Okay, I hope this explains the this point. 57, which means I have half an hour. I will just try and do it in half an hour. So now the comment I've made, and that probably no one understood because it was very cryptic. I said all the complications, all the nonlinearities come from this orange piece. And to appreciate this, we need to think about some simple equations. The hydrodynamic equations are non-linear. And this implies that specific behaviors, e.g. shock formation, are inevitable. To see this, let's consider first a classification of the hydro equations. So, and the classification goes as follows. Oops. Have you lost my screen?
Yeah.
We lost your screen.
I pressed the wrong button. I wanted to get rid of the
okay, good, it's back.
Chat, and I got rid of the iPad. So these two equations here, well, two equations, I say two, but we said it's four. These equations here, nabla mu j mu equals 0 and nabla mu t mu nu equals 0, these can be written in a very generic form as follows. As dt u plus a nabla u equal s. In general, this is true for a large class of partial differential equation, PDEs. So you can write, it's not straightforward, but you can do this. You can write these four equations into an expression of this type, where you have a vector u, which is called a state vector. You have another vector s, which is called a source vector. And of course, you will have certain components. In our specific case, we'll have four components, u1, we'll have five components, u3 and so on, u5. And so we'll have s will be s1, s2, s5. So you have to think that this would be dt of a vector plus the divergence, plus something which is obviously a matrix times the divergence of the same vector, is equal to another vector. Okay, so this is U, and this is S. And A is called the matrix of coefficients. It will, it will have a certain number of components, will be a square matrix. And now, and here is the important point. Let me call, what did we get? 8. Let me call this 9. The set of equations, the set of PDEs 9 can be classified into different classes by looking at the properties of A. In particular, 9 is said to be a linear, let me write it, to be the following. There's going to be a first case where it's going to be said linear if the coefficients of A, or the elements of A, are constant. So this means, let me call it A, J, K. These are equal a constant. Let me use a cut and paste to save some time. It is still called linear, but with constant coefficient. Sorry. This is linear with constant coefficient. This would be linear with variable coefficient. If Aij is not a constant, but are some functions of position and time. So this is number 2. And the last case is said to be quasi-linear. If the elements of A are function of U. Ooh. Components of U. So AJK is AJK of U. We will see some examples that clarify this. Furthermore, this is what I want to say. Furthermore, 9 is said to be strongly hyperbolic if A is diagonalizable with a set of real eigenvalues. And a set of right eigenvectors of linearly independent so in other words, given A, I can always write R minus 1 AR, and this would be a diagonal matrix with components lambda 1, lambda 2, lambda n, where n is the dimensions of our matrix, and this is what we call lambda. And R will be the matrix of right eigenvectors. By that I mean that A Ri, the ith right eigenvector would be lambda I Ri, where lambda I, these are real numbers. Okay, so this is what I want to say. It is possible to show that the set of hydrodynamic equations is hyperbolic in suitable forms. What this sentence is trying to say is that you can prove that a given set of equations, in particular, the ones we are interested in, these equations here, you can show that these equations are hyperbolic if you write them in a suitable form. So you cannot prove that they are hyperbolic under all conditions, because you can always find a silly formulation which is not hyperbolic, and people have used such formulations in the past. But you can certainly prove that there are situations where you can write this as an hyperbolic system. And in such a system, the lambda I are called the characteristic speeds. And I speeds at which signals, or if you want perturbations, propagate. And here is the important thing. Lambda I are real. So these are real numbers. They are not infinite. They are not diverging. So an hyperbolic system is a kind of system that represents physics as we understand it, where signals propagate at finite speed. So the Einstein's equations is one of these systems, and you can show that the Einstein's equations are hyperbolic equations in particular coordinates. For example, Einstein equations can be shown to be hyperbolic in suitable coordinate system. If you remember what Luc Blanchet has discussed this morning, at one point he was writing the Einstein's equations in terms of a wave equation as a principal part, and he was using what he called harmonic coordinates. In such coordinates, you can show that the Einstein's equations behave like wave equations, and wave equations are hyperbolic equations. Okay, so this is a lot of definitions, and in the book you can find definitions of other definitions of other classes which is not just hyperbolic. You can see, when a system is weakly hyperbolic, which is when the matrix A cannot be diagonalized. But let me mention this. 9 is weakly hyperbolic. If A is not diagonalizable. Now, why am I telling you all of this story? Well, because there is an important theorem that says the following: an hyperbolic system is well posed. Okay, and well posed, for those of you who want to, a definition is a system is said to be well posed if the following condition is met. The norm of the solution at any time is always upper bounded by a function which at most is exponentially growing in time with respect to the solution at the initial time. So this is at initial time. I hope you appreciate what is the importance of this condition. This condition is telling us that the system cannot blow up, or if it does blow up, at most blows up exponentially. Okay. The system of equations can at most blow up exponentially. Which is not desirable, but it is still something you can handle. If the system would just be diverging without any bound, then there is no way you can possibly solve these equations. Okay, so the bottom line is that can be summarized in as follows. Hydro equations are hyperbolic, can be written in a hyperbolic form. The second one is that hydro equations are nonlinear. Actually, let me invert this. I think this is more, this should really go after this, because so this one, this is 2, and the third one, a hyperbolic set of PDEs is well posed. So these are the basic concept I have provided you. And now I will come up with some examples of linear and nonlinear system. Nonlinear hyperbolic equations. So we want to have something that resembles the set of equations we've been discussing so far. The example, the relevant example is that of the advection equation. In 1+1 dimensions. So this is a very simple equation, dtu plus v dxu is equal to 0. I'm going to call this 10. This is called the advection equation. This is the equation that is just telling you that the solution to 10 is very simple. And is essentially saying the following. If I want to know the solution at any position x at any time t, all I need to do is look at the solution at time 0 and at position x naught, where this is, I can define this to be u naught of x naught, and this would be u naught of x minus vt. By the way, I should mention this, v is a constant. Okay, so to have an idea, suppose that you are in a space-time, t and x, and you want to know the solution at this point here, x and t. You would like to know what is the value of u at this position, okay? So you would like to know what is u at xt, and all you have to do is go back in time and go back in space to the direction given by the position x naught, which is x minus vt. Okay, so that's all there is to know about an advection equation, and that is why it's such a simple equation. It's a linear equation. In other words, let me write this differently. The solution is simply advected in space-time. Along what directions? Along the characteristic directions. So we can see this in a different way as so. Let's take the total time derivative of u. So this would be just du dt, and this would be dtu plus v dxu. Sorry, this would be dx over dt dxu. And if this is going to be 0, if v is equal to dx dt, or if you want, this is going to be a certain direction, lambda equal a constant. So that is why we talk about characteristic direction. V, that is this slope here, is setting a velocity in a space-time diagram. And so given a solution, an initial solution here, the whole solution will be simply translated in space-time at a new position. Sorry. Will be simply translated in space-time, and all of these pieces will just be moved from one position to the next. Shouldn't do this. So this is V dx dt. Well, 1 over the slope of that. This is t, and this is x. Okay, so imagine that we take as an example u be just a sine wave. Then what you have to imagine is that if this is x and this is t, sorry, this is not x, this is that, this is u. Okay, so u is just a sine at t equals 0. Let me also do t here. I have a given sine wave. Well, each piece of this sine wave will be just advected. I should okay, I forgot I can copy here. So I can copy this function over here, and then I just join the different pieces. Okay, I don't know if you can see this, but this is the same as in this space-time diagram. Okay, maybe I highlight with different colors the different pieces. This is the central part of my solution. Okay, so a linear hyperbolic equation is easy to understand. Let's consider now the simplest case of a nonlinear equation. And I start from this equation here. And the only thing I change is here. I replace V with U. This is called the Burger's equation. And it's nonlinear because, if you remember, AJ, in this case, there's just one component, so it would be A11, is actually U. So it's not a constant coefficient. What are the implications of this nonlinearity? Well, they are the following. Let's take again this expression over here, the conservation, and let's take so variation. Then dt of u, this would be dtu plus dx dt dx u, and this would be equal to 0 along directions lambda, which would be now u of x t. Okay, so the directions are no longer all the same. Okay, this will be functions of position and time. And so these as the important difference that if I now want to create the equivalent of this guy over here, then I don't have that this is no longer true. Actually, I will have the following. That, let me, there's going to be the characteristic speed will be different in different positions. And in particular, it is possible that all of the characteristics converge in one point. Characteristics converge in one point, and a caustic develops. Okay, when a caustic develops, then the solution is no longer unique, and discontinuities can develop. Let's think about what happens if we were to plot u as a function of position at different times. And we start again with a very simple smooth functions. We start with a sine wave. Oops.
Luciano, sorry, it's just to tell you that it's 18:30 almost, and so it will be time to conclude soon, unfortunately, most unfortunately.
Well, I'm planning to close in a couple of minutes. I just want
Okay, perfect, great.
So this would be the solution at t equals 0. The solution at a different time would look slightly different. In particular, the shape will no longer be preserved. The shape will look more like so. And at a later time, it will look more like so. And at a time which you can actually estimate analytically, you will become like so. And this is called a shock or discontinuity. Okay, let me try to wrap this up. In hydrodynamics, not in hydrodynamics, in nonlinear equations, caustics can develop even from smooth initial data. i.e., shocks are inevitable, and numerical schemes have to be developed to cope with this problem. And the numerical schemes that are used to cope with this problem are called HRSC. High resolution shock capturing methods. Okay, I will stop here, and I will. I hope I can use the questions to fill in some of the details I couldn't. This is called wave steepening. because the wave becomes steeper and steeper up until it leads to a shock. Okay, so I will stop here. Go ahead with questions if you have any.
Thank you very much. First, there were a couple of questions I forgot to to tell you before. When you discussed you introduced the equation of state, I have to find them. One was, does the equation of state connect to a conservation law? If not, what physics it relates to?
So this is a very good question. Where does the equation of state come from? How do I derive it? It's not a conservation law, because the conservation law I've given you. The equation of state has to come from a knowledge of the microphysics of the system. It's the microphysics of the system that will reveal how the pressure depends on your composition or your energy density. And this is because the equation of state does not appear in the hydrodynamic equation, because the hydrodynamic equations are effective. It's an effective description of physics. It's ignoring microphysics. It's putting it aside, and it's just saying, okay, when it comes to microphysics, you will have to tell me, because my set of my effective theory does not describe this. Now, this effective theory comes from Boltzmann theory, from Boltzmann equation. And in Boltzmann equation, you would have a complete description, because the collisional terms in the Boltzmann equation, those are the ones that would allow you to obtain an equation of state, and so a relation that is otherwise missing. So in summary, Boltzmann is the true theoretical description. If you want to go to hydrodynamics, which is very convenient, you have to renounce to something, and that's the macrophysical knowledge. And you can supply this knowledge through an equation of state. More questions on this part that I've just.
Yes, if there are questions about the most recent. The last part of the lecture, please go ahead. Otherwise, there was also another question concerning this part about the equation of state. Is P the same function of rho at linear and non-linear order? I'm not sure I understand the question, but can you answer?
Yeah. So yeah, there is no order in P. P is an expression that relates rho at any order, because there is no concept of order. I mean, there is different behavior. The pressure can be the relation between P and rho will be in general a non-linear function. Okay, so that you might have that pressure is very weak at certain density, is very high at other density, and where these density are, whether it is low or high, depends on the microphysics. But it's a generic function, non-linear function. The example I was giving you for cosmology, P equal WE, this is really the simplest thing you can do, just because you're so desperate you don't have any other intuition about the relation between P and E. And that this description allows you to describe a radiation fluid or a dust, and so you just try it out.
Okay, there is a question with the following question. If the fluid is not a single fluid, is one additional equation coupling the two fluids sufficient to solve the system?
That's a very good question. And what you're talking about are called multi-fluids. You can have different species. And you can think that the multi-fluids are completely decoupled, and then you have just a copy of all the equations I've given you for any species that you want. Or you can think that the fluids are perfectly coupled, in which case you have a very simple prescription that allows you to go from one fluid to the other. If you think about radiation and matter, then you can think that once you know one, you know the other, and the only difference is the contribution in the pressure. The pressure will be the sum of the two, and you know how to relate one to the other. complicated situation is the intermediate one between these two I've mentioned, where you have many fluids or two fluids, just to make it easier, and they are weakly coupled. So there is some exchange of momentum between the two, and then you need additional equation that clarify and express how this momentum is transformed, is transferred, and so is the energy. Again, if you look at the book, you will find more information also about these multi-fluids. More questions?
Yes, more questions are arriving, so you can read them. So, for instance, you describe shocks as a generic feature of nonlinear hydrodynamics. Are there conditions on A where shocks are avoided?
That's a very good question. It's not on A. You can change the equations. Let me show you how you do it. Let's take this equation, okay? And let's put here another term. Let me call this epsilon dx squared u. Okay. So when u is smooth, then dxu is much smaller than dxu. And so you have, the standard nonlinear equation. But when u steepens, okay, then dx squared, the second derivative, can become much larger than the first derivative. And then you have a parabolic equation or a diffusion equation. Okay, so if we go back to this example here, when we were steepening, then you can imagine that before steepening, there is going to be additional terms, the ones coming here on the right hand side, that will want to smoothen out this profile, so that the profile will actually look like so. Okay, and so you can avoid shock formation by introducing the additional terms, which are dissipative terms. These are dissipative terms. And of course, in ideal fluid, in perfect fluids, they are absent, and so shocks will just develop at a full strength. Let me also, I like to make this example for those of you who have problems grasping this example of the wave steepening. Imagine that you are all traveling on a highway, and that you start with a train of cars, and they are all equidistant and all moving at the same speed. This is a situation like so. There's going to be a first car, and there's going to be a last car, and they all move at equal speed because their speed is said to be constant, and so they will all arrive in the same order: the first car, the last car. But if for some reason, and the reason is that someone wants to go faster than the other, say the third car wants to go faster than the second car, then what happens, very well, they're going to crash. Okay, either because the third car will hit the one in front of it, or because the one in front will be slower and be caught up by the next one. Okay, so think of this example of the wave steepening as the one you would encounter in the case of flow propagation, traffic flow propagation. In fact, traffic flow equations are very similar to those of hydrodynamics. More questions?
Yes, a couple of more questions. So for quasi-linear class, is there any constraint on the nature of function that the matrix elements A, J, K can be of few components, or is it arbitrary?
No, so that's a good question. In my classification, I've left out a system. And this is a system which is actually called non-linear, okay? We physicists call this system linear. So what mathematicians call quasi-linear, we physicists call non-linear because it's already bad enough for us. But mathematicians, they are not afraid of anything. So they call non-linear system a system where A, J, K is a function of the derivatives of U, okay? So that's for them is a nonlinear system. And so that's the complete set of equations, or well, the complete classification system. And there are no other limitations. You can build whatever system you want. Now, let me exploit this to make a comment. Why did I say, why did I say these are nonlinear equations? I need the, yeah, okay. Let's go back to this point. Look, this is the Burger's equations, okay? Or if you want the advection equation. The advection equation is dt u plus v dx u equal to 0, okay? So if this guy is equal to a constant, then you have a linear equation. dtu plus u dx u, we've seen this is a nonlinear equation. That's exactly what we have here, because this is u, okay? It's the same object that we're taking a derivative of. And that is why the hydrodynamic equation, in particular the Euler equation, gives rise to shocks. More questions?
Okay. Yeah, so I think we can take a last question and then we have really to stop because it's getting late. Is there any way of taking the fluid limit of Boltzmann equation so as not to average out too much and keep the microphysics contained in the right-hand side kernel?
Hold on, I don't think I understood your question. I'll read it. Is there any way of taking the fluid limit of Boltzmann equations so as not to average out too much and keep the microphysical contained in the row kernel?
In the right-hand side kernel.
The right-hand side kernel. Well, yeah, I don't think, it is, the fluid limit is convenient for one thing, is that it is easy. If you want to use the Boltzmann equation and you just use the Boltzmann equation, you don't try to come up with a fluid description. And, that's not too bad. Most of the time, the fact that you don't know the equational state, but can be derived from first principles. So it's not that the equational state is, hanging from thin air. It comes from very advanced first principle calculations. For instance, when you want to study the equational state of a neutron star, okay, it's not that we just invent an equational state. Well, sometimes we do, but most of the time we try to use the most realistic equational state that comes from our next door nuclear physics colleagues who spend their career thinking about what is the most correct way of expressing the interaction between nucleons using, nuclear physics theory, using experiments and so on. So the fact that we have to supply an equational state is not the end of the world for someone who wants to do hydrodynamics.
Thank you,
Okay,
Luciano.
so thank you. I cannot resist to ask the very last question, and then we stop. So are shocks physical or is it a bad modeling?
That's a very good question. It depends on are you, first of all, shocks do not exist in reality, okay? It's a mathematical abstraction. If you there's, you know, if you think about, like, where is my steepening curve? Yeah, here, okay? So the situation where you end up with a double value function, so that this and this correspond to the same spatial position x bar, that's just in the mathematical limit. Reality will be such that even if there is an absence of dissipation, there's still going to be that this surface will have a certain thickness. And this will be the mean free path of particles, because particles are, at the end of the day, our constituents. You know, don't forget where we started. We started from here. We started from, I've lost where is that. I remember that I did a little, here. We started from this description, okay? We have a little fluid element where we have particles. We're thinking that particles are moving and they are scattering, and they have a mean free path between scatterings. So even in the most extreme case, the thickness of a shock has to be larger than the mean free path of particles. So the answer is no, they don't, you know, physically, they are just mathematical abstractions. But if you don't treat them as those mathematical abstraction, you can't go very far, okay? So they are actually very important because they allow us to pose boundary conditions and junction conditions. So the existence of shock is useful, even if in reality, you know, they don't exist as discontinuities of C infinity class.
Okay, thank you very much. I thank you on behalf of all participants. And I think we can stop here. For all of you who are still present, thank you also. And maybe hopefully we meet tomorrow at 10 for the continuation of the program. Goodbye.
Thank you for listening in. And so Guillaume, if there are more questions than the students, I mean, in principle, if I was there, I was supposed to meet the students regularly every day, and so questions maybe would come up
Okay.
offline.
Thank you very much. So also there is this gathered town, I don't remember how it's called, where you can also try to go and meet people more informally. The link is given on the program. So it's, I tried it just to see how it works. And indeed you can see posters, meet people. It is
okay. I've never used it, so I don't know, but
you can try. I mean,
yeah.
But also, I would like to ask you whether you would agree to give us your slides so that we can put them on the web page of the program.
Yes, of course. I will just clean them up a bit because
Sure. Then you send them to me, and I will put them on the web page as soon as I get them. Thank you.
Okay.
Thanks
have a nice
again.
evening. Yep.
Goodbye.
Bye-bye.
Thank you.
Yep.
Thank you.
Goodbye.
Ciao.
Can you please stop the recording? Hello, can you please stop the recording so we don't have to cut it like this morning? Excusez-moi, est-ce que vous pourriez arrêter la captation? De sorte que nous n'avons pas à couper L'enregistrement comme pour ce matin? Allô?
Allô?
Oui, est-ce que vous pourriez arrêter l'enregistrement, s'il vous plaît?
Ok, je vais vous le faire alors. D'accord. Bonne
Merci.
soirée.
Merci, bonne soirée.